All right, hello everyone. I'm Jason Wu, and it's great to be here to present the never-ending learning of user interfaces project. And this project is something that I did with my collaborators at Apple, Rebecca, Eldon, Amanda, Jeff Bigham, and Jeff Nichols. So now, more than ever, there's been a growing interest in how machines or agents can robustly understand and operate user interfaces. And there are a lot of things that they need to know in order to do this. So these are things like, hey, what are the UI controls on a screen? How are these controls arranged to display information or functionality? And finally, well, what can I actually do with this UI? Or in other words, what are its affordances? And a lot of research has gone into building data-driven models to answer these questions. And this has led to great systems for accessibility repair, task automation, and design tools. But right now, we as humans, we have to teach the machines how to do these things by providing tens or even hundreds of thousands of annotated UI examples. And as you might imagine, this process is really time-consuming and expensive. Widely used data sets currently out there has been estimated to cost tens of thousands of dollars to collect and is several months of human labor. So this makes it prohibitively costly to continuously update the data sets to include the newest versions of apps. And this is really important because UI designs change all the time between apps and even OS versions. And finally, human annotation is surprisingly error-prone for a lot of UI semantics. Previous work has shown, for example, that if you ask human annotators to annotate which elements are tappable from a screenshot, this actually leads to really high rates of disagreement because of ambiguous visual signifiers. So to give an example of this, I wonder if you can guess all of the interactions supported by these UIs here. So some are more obvious than others, right? So we can probably guess that, hey, we can tap on this toggle here to toggle it, and we can also tap on this change button. But in fact, there are many more. So for example, we can actually drag these list items to delete them. And actually, depending on where we tap on them, different things will happen. So we made some observations here, right? First is that it's just difficult to annotate user interfaces at the training stage if we only have these screenshots. And more importantly, right, as a human, we don't need to learn from annotated examples, right? And a lot of times we actually eventually learn how to use apps by just playing around with them and discovering functionality. And so the question is, well, how can we get machines to do the same thing? So towards the first goal of going beyond screenshot annotation, we designed some labeling heuristics that basically take segmented video clips or screenshot sequences and inferred effects of interactions. So for example, we can start with an initial screen, then if we want to learn about one of the elements, we can simulate a tap on it, right? And if the post-interaction screen is a new screen or has some other kind of visual change, then we can infer that that was most likely tappable. And this is just another example, right, for draggability. And what we expect basically is if the element is draggable, it can kind of like follow our finger. So that's a heuristic for draggability. And towards the second goal of learning more like a human and discovering things over time, there's actually this framework in the machine learning literature called never-ending learning. And this is interesting as there are four kind of main goals in this framework. As the name suggests, of course, right, the main thing here is that we want to be able to learn over prolonged or potentially even unlimited periods of time in a self-supervised way. And another thing this framework gets us to think about is strategies to kind of use previous knowledge to help with further learning and also avoiding model performance stagnation. So we use these four goals as kind of, we use these four goals to guide how we implemented our system and also how we ended up evaluating it. So we built the never-ending UI learner, and it's a distributed crawler that automatically installs real-world apps from the App Store and crawls them. And from a high level, right, it has this, it gets a lot of real devices, installs real apps to them, and then continuously crawls them by attempting various interactions using either a random policy or a policy that's actually driven by model confidence. And using these observations from the interaction, we're actually able to generate labels. These labels are then sent back to a central server, and they're used to update these models, these UI semantic models. And these new models are actually pushed back into the crawler itself, so it affects the behavior of subsequent crawls. Each crawler is equipped with some machine learning models that predict UI semantics, and we actually designed some new architectures for this that was more efficient for this style of online learning. The key here is that we basically tried to minimize the number of trainable parameters by adopting what's called a multi-headed architecture, and this is basically desirable because it improves learning efficiency and also stability. To give you an idea of how, To give you an idea of how all this works together, here's some footage that we saved from our crawler running on some apps, and we can see in this sped up footage that it's basically attempting to tap and scroll and drag elements to learn what's on a single UI, but more than that, it's actually exploring to new parts of the app to get more training data, examples for itself. Okay, so how well does this work? We conducted a series of experiments where we ran our crawler on for 5,000 device hours, where it performed over 500,000 actions on 6,000 real apps. And our primary question was, well, how well does the system perform over time, right? This is a never-ending learning system. And one of the other goals I mentioned earlier for never-ending learning was that we want to look at strategies to reduce model stagnation. So we wanted to investigate some of these different crawling policies. And so it's important to also know for these experiments, we basically validated them on a held-out set of apps where we asked human annotators to annotate recorded videos of those apps, and as opposed to screenshots. So we used our crawler to train 3 models in total. I showed you the first 2 affordance prediction models, and the third is something called a screen similarity model, which basically tells us if the crawler arrived at a new screen, which is helpful for some of those heuristics that I showed you earlier. But actually, this model itself is improved over time as well. And each crawl epoch on the x-axis here basically represents installing each of the 6,000 apps once, and it's actually reinstalled every epoch because it can actually change in the meantime. And you can see the crawler learned the tappability and draggability models completely from scratch without any human labels, and actually continues to improve over time. And for the screen similarity model, again, we started from a pre-trained model from existing work, and we were able to improve that. And for the crawling policies, we tested we tested one policy that was randomly selecting an element to learn about, and there's some variations of a technique called uncertainty sampling, where we can select samples based on low model confidence, for example. And in our experiments, the simple random policies seem to perform the best, but I think there are probably some parameters that we can tune for the uncertainty sampling. What we noticed so far is that if the model always chooses the same types of low confidence samples, it could lead to a little bit overfitting in the next batch. Okay, so to wrap up, our work is motivated by the interactive nature of user interfaces and using that to the advantage of machine learning-based UI understanding. We applied the framework of never-ending learning to user interfaces to let machines use and learn to use UIs more like humans do. And we implemented our system and let it run for 500,000 actions on 6,000 real-world apps, and the resulting models learned from these interactions are more accurate than ones that you could get from human annotated screenshots. And thank you. I'm open for questions.
Hi, Judy Kong from University of Washington. Really, really interesting work, and I love this talk. Thank you so much. I really like the idea of using the video clip and see how it changes. after this crawler's action. So I wonder, how do you differentiate, let's say if there is a GIF or some animation inside an app, whenever you see that visual change, how does this model differentiate between, or how does this model understand whether this is caused by the crawler's action or it is some kind of non-significant visual change?
Right, that's a great question. So that's a detail I kind of skipped over a little bit briefly, but in the heuristics for these labeling, interaction labeling, we actually establish a baseline. So there's actually multiple screenshots taken there. So if there was a GIF, right, we can know like which regions of the screen are changing before the interaction happened, and we can kind of use that to rule out some of those false positives.
Thank you so much.
Yeah, thanks.
Hey, great talk. One quick question is that for drag, especially like sometimes super weird. For example, one of the example app you showed there is like the Tips app in iPhone, and the Tips app, if you drag a little bit towards the left and right, it will change the screen, so it shows that it's scrollable, but it doesn't necessarily navigate to the next screen, right? So you have to drag for long enough, and it would snap to the next screen. So, like in your system, do you have like a long drag, short drag? Like how do you distinguish between them?
Right, that's a great question. So yeah, actually it turns out depending on how much you drag, different things can happen too. Our heuristic, I think we had a set ratio that was basically like a ratio of the actual element size. I think it could be pretty easy to extend this, like we can have like a multiple heuristics attempting like different levels of drags, right? So that's not something we tested in this particular version. But yeah, like I think for a lot of the drags, it was basically like half of the element width, and that was enough to detect.
And then you basically observe, for most of the cases, that will trigger, if it will actually have an element change, it will trigger element change.
Trigger an animation, sorry?
Like a navigation. So when it is
so the drag doesn't necessarily result in navigation. It'll just follow your finger. The tapping one, it might trigger navigation, like the dragging.
And then when, for example, in setting as if you drag down a little bit, you don't consider that to be a navigation.
Oh, like a scroll?
Scroll, yeah.
Yeah, we also count, we have vertical dragging, which is basically scrolling potentially, and also horizontal dragging, which is like the dismissing. Those are kind of separate heuristics. Yeah.
Cool. Thanks.
Thanks, Jackie.
Maybe just one quick, and then you wanna come up?
Okay.
James Egan, Institut Polytechnique de Paris. Have you considered, it looks like you're using just screenshots, so the surface representation. Have you thought about extending this with deeper, for example, you have access to the Windows server stacking levels. Have you considered extending some of the training model to take that into consideration?
Right, so if I understand correctly, you're asking like, what about like the metadata maybe of apps?
Right.
Right, so that's a great
metadata in just the way that the the various UI components are stacked on top to draw the screen.
Right, kind of rendering information. Yeah, so that's a great question. This is actually a huge theme in accessibility where that information can be really useful, but it's also not always available, and that's also one of the reasons why a lot of apps are not accessible to screen readers. So in our particular work, we're kind of focusing on like pixel inputs, and it's also kind of useful for like at the design stage where you might not have something that's literally rendered yet. We're just drawing things. So it could be useful, but it also might not work for some use cases. So that's why we looked at this.
Thank you.
Thank you, Jason.